Well then, good morning everyone. It's my pleasure to introduce Stratos for our first keynote speech this morning. And the title of the talk is Soon Everyone Will Be a Data Scientist or Data Explorer, and what systems will they be using?
Thank you. Okay, so good morning. We're going to be talking about data systems. So I'm going to try to convince you how data systems in the future should be more plug-and-play, self-tuning, and adaptive. So I want to try to motivate big data. You know about that, but just to set the stage of the vision that I'm looking for the future. So you know, as much as the whole story about big data today is quite overwhelming, we try to rethink how we design fundamental algorithms and data structures in computer science, for example, how we train people. Everybody's looking for data scientists. I think in the future this is going to be even more crazy because we're quickly heading towards a future where everybody's going to be wearing or holding or even being injected with devices that, you know, they create data all day long about everything that we really do in our lives. Like every step we make, even every breath we take, we're going to be recording it. And so in such a future, basically data production is going to go over the roof. And then how are we moving, how are we storing, how we're analyzing this data? And this is how I like to say that everybody's going to be a data scientist. And I'm exaggerating a little bit with my slides, but the point is that not that everybody will really be doing statistics and analytics and all that, but that data systems and algorithms and all our data techniques are going to be in the critical path of everything we do in our daily lives. Okay? And then either directly or indirectly, everybody has to be a data scientist to be using this kind of systems. Okay, so the question that I'm trying to ask is, in such a future where everybody is connected, where everybody is relies on data and data-driven systems every day, how should these systems look like? So what are the challenges? I think you all may have slides like this in your presentations. I'm sure you know about that. I just want to emphasize that it's not only about size. For example, in the data systems community, one of our biggest conferences is called Very Large Database Systems, and you know, it's been held for 40 years. And I'm sure, you know, at least this is true for all of computer science. Data size is not really the major challenge, but the other three, and the combination of the other three with size. The one thing that I really want to stress is big data exploration. So exploration is when we have a big pile of data and we just want to find something interesting in the data. So we don't know what we're looking for until we actually find it. And when we find it, we say, oh, this is interesting. I really want to dig in and try to learn more about this. Now, if you think about this, data exploration is fundamentally different compared to what we have been doing in the past 50 years in computer science. Typically, it's about, you know, we know exactly our data, we know exactly what we want to find out in our data, and then we design techniques to do exactly this thing in an optimal way. Now, let's try to compare, let's say, an international financial organization, like an international bank, with what an astronomer wants to do, or with what a biologist wants to do. Okay? So in science, for example, we're looking for something interesting, even though we not know what we're looking for. In a financial organization, we know what we're looking for, and we design optimal algorithms for this task. So this is fundamentally different. Okay, so that's the stage. And now I'm going to split the presentation into three parts. The first part is going to be briefly about what is the status in data systems today. The second part about what we should do in the future, what is the vision for future systems. And then I'm going to briefly try to pitch to you a couple of our research projects that we're working on with students and friends and colleagues. Okay, so status. So data systems already, they're sort of prevalent in our daily lives. So you know, you're trying to book an air flight, you're going through a data system. You go to the grocery store, you go through several data systems. Anything you do, you're going through data systems, basically. Now, what is a perfect data system? So the original premise was that data system would be a black box. Okay. So basically, and it's built around this wonderful concept, which is declarative interfaces. So basically, you just, as an application or as a user, you just say to the system what you want, and the system will figure out how to do it. This is such a simple concept, but it's so powerful, and this is exactly what allowed us to be able to use data systems in our everyday life today. Because by having this concept, we can build applications on top of data systems that they don't have to know about all the internals, all the magic that happens inside the black box. You can just build applications without having to know about that. You only have to worry about your application. And then a data system should do all sorts of other very complex stuff, such as being able to process multiple requests at the same time. Nowadays, even thousands or even millions of requests at the same time. Be able to compute correct and complete results every single time. So when you go to, let's say, to your ATM, your bank, you would like your bank account to have correct results every time. You would like it to be secure, and you would like it to be robust, and so many other features that create such complexity. Now let's try to see inside the black box. Inside the black box is basically fundamental things from computer science. It's a sequence of, it's a huge array basically of algorithms and data structures. Okay? So data structures, different ways about how we can store our data, and algorithms, all sorts of different ways of how we can manipulate our data. And every time that we give a request to the system, what basically happens is that the system has some high-level logic to decide that, oh, I should take this data from this part, from this data structure, and push it through a set of the algorithms that I have inside my system to create the result. And actually, choosing the proper algorithms, figuring out what the interfaces should be between these algorithms is one of the really fundamental challenges. And that's one of the beauties in doing research in data systems. It's not just about, let's say, figuring out how I should optimize this specific algorithm and make it very fast. You really have to worry about the whole thing, because you might come up with some, let's say, some very smart ideas and optimize one of the little boxes over there, but then overall your performance, how fast you can process queries or how energy efficient your system is, can deteriorate. So you really have to worry about the whole stack. And then nowadays, we also worry a lot about hardware. Systems run on top of hardware, and hardware becomes more and more complex as the years go by. So one fundamental challenge that has happened in the past few years is that nowadays we don't only worry about CPU time, we worry a lot about, as we call it, the memory hierarchy, the complexity of the memory hierarchy and how data moves through that. So while in the past we're trying to optimize about CPU, now we're trying to optimize about the memory hierarchy. And it's very typical that you take a standard algorithm and you redesign it such that it becomes a bit more stupid, let's say, in terms of how much CPU is using, so it does actually more steps, okay? And this is better as long as you can actually read less data, okay? Okay, so let's see. So data systems are wonderful in many different ways today. But if you look them, I will try to convince you that if you look at them from the perspective of big data exploration, data-driven systems, data arriving quickly, you want to react fast to data, they're truly heavy and they're truly blind. And the elephant is sort of an internal joke in the data systems community, representing old and traditional systems. Okay, let's build a timeline that will show us what it takes to build an application once we have a system. So now you have your data, and the first thing that you have to do, you have to copy your data inside your system. So let's say you have 1 petabyte of data. Now you have to copy this inside your system, and now you have 2 petabytes of data, which doesn't sound very good. The next step, I mean, you do that because then the system can actually manipulate the data in its own way and do things very efficiently. But the more data you have, the harder this problem becomes. The next step is even trickier. The next step is about tuning the system. So systems can become so complex and that have put so many knobs in there and options that somebody has to tune the system. Okay, it doesn't just work. And tuning means that you tune the system based on your data and what you want to do with your data. So already this contradicts the data exploration goal. And only after you do all these steps, only then you can query the system with good performance. And now you would wonder, oh, this is only maybe 2 or 3 steps. How bad could this be? Even for medium-sized applications, this thing can take months to get right. So it's really not a simple problem. And data systems community has been working on this problem for 50 years, actually. So really, this is a very complex process. It's a time-consuming process. And it's a process that requires you to have knowledge about what exactly are you doing. So this is completely the opposite of data exploration. And here is where the original premise that we discussed about the black box, now this breaks. And what happens is that we put database administrators, as we call them, well, human beings, human experts, inside the loop. So it's not a black box anymore. Between users and applications and the systems sit human experts that deal with all the tuning and the loading and all the little expert steps that you have to do to make this work. So this doesn't just work anymore. And if you see the trend now with more data-driven applications, what happens is that we don't just have a single system, we have multiple systems. And by multiple, I mean a lot. A lot of different kinds of architectures. And architectures, if you remember the original slide where we saw about what is inside the box, the black box, an architecture is a collection of algorithms and data structures. So for different applications, we better have different kinds of algorithms and data structures and different kinds of ways to interconnect them. And that leads to completely different systems. And as we create more and more applications with more and more data-driven requirements, we create more systems. And then we create more requirements to have different kinds of experts to tune those systems. So in the end, we have right now such a complex setting, such a complex environment, where we really need to have all sorts of experts in the loop, and we cannot just use systems. We not only have to tune the systems, but we also have to decide what kind of system we should use. Okay, so let me tell you now about what I think we should be doing. So the premise of my work is to always designing systems which basically they're not like what I described before, but instead they're designed from the bottom up towards data exploration. What this means is that going back to this simple model of the black box. Okay? So basically, systems should just work without having to have any workload knowledge, invest any idle time, or having any kind of expertise whatsoever. It should just be, again, a black box like the original data systems that people envisioned back in the 50s for the strict static scenarios that we had back then. And we should do the same for the new data-driven scenarios for data exploration. And then the users in the application should just be considered as explorers. Okay? And here's a typical interaction that we should be able to support. So the users should just be able to say, this is my data, and this could be any kind of data in any kind of size, and it should be as simple as that. Just point to the data. And then just be able to say, tell me something interesting, and by the way, please do this super fast. Okay? And again, you should not have to declare something, you should not have to define something in some complex language, just tell me something interesting, or show me something interesting. And then there should be a little bit back and forth, and the user should be part of this loop, indicating and giving feedback to the system about which parts of the data are interesting, and then together they should navigate to the interesting parts in the data. So that's my most important slide. And let's see, now let's build a little bit on top of that. So now if you try to think about some concepts based on this challenge, you could say that systems of the past, well, systems that we have now, they're mostly focused on how we make things very, very fast. Okay? And that's a very noble goal, and we should keep doing that. But systems of the future should be more about how we find fast what kind of queries we should be asking. Okay? Because the moment we have so much data, we cannot just process all the data fast anymore. It's more than what we can afford. So we should really have smarts to figuring out where we should focus and then do the processing. So this boils down to what we like to say is that minimizing the data to query time, and that's a huge challenge. So minimizing the time from the moment you have your raw data, so data without any kind of structure, just plain data, to the moment when you actually have some knowledge out of the data. Okay, so general directions of how we're trying to approach this. Basically, we start going through every little step or challenge inside data systems, every little algorithm and data structure, and we try to give it these properties that you see here. We try to make it auto-tuning so that just we don't have to turn any knobs in there, just it should take the proper shape by itself, take the proper metrics by itself. It should be adaptive, it should be able to understand what we're doing and adapt to that, or how the environment is, or how the hardware is. It should be interactive. Every time we do something, we should just get a response immediately, very fast, not wait. And definitely should be plug and play. So it should be able to just start working without us having to do anything about it. Okay, let's see a couple of examples now. So first example of a research effort that we're doing, we call it adaptive indexing. And you see this word adaptive a lot. So indexing, this is the original timeline that I showed you about how it is complex to use data systems today. Indexing is about the middle part, the tuning part. So usually in this part, we decide what kind of data structures we should build on top of our data. So think trees, bitmaps, any kind of data structure that can actually allow us to go through our data faster. And if we get this right, performance meaning data access, extraction of knowledge can be orders of magnitude faster than if we don't have this. Now, what's the problem? The problem is that we cannot just go ahead and build any index possible. We don't have enough space, we don't have enough time for that. So we have to make decisions. So we have to decide, for example, which indices we should build, what kind of properties they should have. Should it be a tree, should it be a bitmap, how it should look like, on which parts of the data we should do that, and also crucially when we should do that. Okay? Because having an index in a system, it's not for free. For example, when you have updates, you have to maintain the index and keep it updated. So how do we do this today? So we're building another timeline now. So in order to make these decisions, the first thing that we have to have is sample workload. So this is a representative set of our data and a representative set of the queries that we're going to do in the future. So we really need to know exactly what we're doing, which has no connection with data exploration. Now, once we have that, we do what we call what-if analysis, which basically is a process where we say, what if I had this index in my system? What the performance of my system would be like if I would do these queries, and so on and so forth. And you do this for every single data part, for every single option that you have about indexes, and then you come up with a set of indexes that you think it's best for the things that you're going to do with your system. And then you actually go ahead and materialize those indexes, so you create them for real. And only then you can query the system. So again, you see that this is a very complex process, it's very time-consuming, and it's completely the opposite of data exploration, and this is why we need the human experts in the loop. So what can go wrong here? If you start thinking about all this process and thinking about data arriving in big quantities and arriving quickly, so here's just 4 examples of what could go wrong. So first of all, with bigger amounts of data, there simply might not be enough space to index all the data, which is a very common case. Now, more interestingly, there might not be enough idle time to go through the indexing phase. Okay, so the data arrives quickly, you're going to create indices and you're going to query immediately. Well, you don't have enough time to create all those indexes. Okay? Or even worse, that you think you're going to do these queries, and then you start indexing based on this knowledge that you're going to do these queries, but by the time you finish indexing, now you realize that different data parts are indexing, so now you want to build different indexes. Okay? And also, what this means is that now you have all those previous indexes laying in your system, which are actually big overhead. And then, especially if you think about, and you can think more scenarios like this, but also the last one is interesting. So the fact that, well, not everybody can actually have database administrators and paying them six-figure salaries just to be able to tune their system. I mean, companies can do that. Can scientific groups do that? No, and that's a big reason why they don't use data systems and why they have to rely on manual tools. And then you can have energy constraints into mind and all sorts of things. So here's an idea. We call it DB cracking, and it's the first instance of adaptive indexing in DB systems. Basically, as I said before, we're dropping all the initial requirements of original requirements of data systems, and we're building data systems which are adaptive, behaving in an adaptive, incremental way. Now, the basic concept is that we take all these decisions that we originally made. Just conceptually, we take all these decisions, and instead of making them during the initialization phase of a system, we just shift this to the query processing phase. What this means is that when you start initializing a system, an application, basically you have nothing to do. Okay, you take no decisions, you do nothing, zero cost. And then, as you start using your system, the system should be able to adapt by itself and become faster and faster the more you're using it. Okay? Now, the basic, let's say, motto that we have and guideline that we use in this design is that every query that we get from the outside world, so from users or from applications, we treat this query, this request, as an advice on how the data should be stored. Okay? And this is all that it is, creating auxiliary data structures, creating algorithms that touch the data. It all starts from how you store your data, how you lay your data on disks, in memory, in CPU registers, and so on and so forth. So basically, instead of making this decision for the applications in a static way, we let the applications make this decision on the fly by the request that they give to us. So let me give you, data systems are super complex things. I'll try to give you a very simplistic example. So think of this as, just to give you the concept, so think of this as a typical relational schema where you have tables and columns and so on and so forth. And we'll try to do a simple example for just one of the columns. Okay? So let's say this is a column that contains just integer values, and we'd like to do this very simple SQL query, which basically all that it says is, from this column, give me everything that fits within a specific range. In this case, between 10 and 14. So we have an array of integers, basically, and we're just going to figure out all the values which are within this specific range. Okay? And this is a super simple operation, but it's an operation that happens actually, on any kind of analytical query that you imagine you might do. So it's a basic filtering operation. So what would be a great way to do this? Well, we could just go ahead and sort this column, and then if the column is sorted, we can just do binary search. Okay? And then the results will nicely be in a contiguous area in the column, and we have all sorts of interesting ways to do nice sorting. We have all sorts of nice sorting algorithms depending on the size of the data, depending on the hardware, and all these things. But the problem is that, again, if you think in the analogies that I talked about before, sorting takes time. Okay? And it takes time, and it has also side effects. One of the side effects, for example, is that, well, if we just went ahead and sorted this column and think that this column could be big, this could take a lot of time. But also, now that this is sorted, when we have updates, now we have to maintain the order in this column. Okay? So we have to really go and place the new values if we have updates, or remove new values from very specific areas, because we have to maintain the sorted order. Also, this column it's not just an isolated column, it's part of a system. So it's part of a sequence of columns that belong to an entity, to a table, to a relational table. So if we just went ahead and reorganize this column, this has side effects on how we can access the other columns in the system. Okay? So really, if we're doing such actions, we really need to know that this is going to be useful in the future. And how useful it is, it really depends on how many times we're going to access it. So again, it goes back to having workload knowledge, knowing that this kind of queries are going to come in the future. So here's what we can do instead of just blindly sorting the data. So we do zero actions before, and the moment we get the query, we start physically reorganizing the column. So here what we do is that we take all values which are smaller than 10, so smaller than what the query requested, and we shift those values to the first part of the column. Okay? Then we put all values which are between 10 and 14, and then all values which are bigger than 14. So basically, we used the range that the query requested. We used this as an advice of how the data should be stored, and we went ahead and we reorganized the column physically to map this request. Okay, so we used the query as an advice of how the data should be stored, and we did that just when the query arrived during query processing. And basically, we achieved the same effect that we had with the binary search. We just collected all results, all qualifying results in the same contiguous area in our column. And that basically answers this particular query, this particular operation. But crucially, for the whole picture of the system that tries to adapt and be auto-tuning and so on and so forth, now we have knowledge about how our data is organized. Okay? Because we also built little navigation structures on top of that. So we know we have basically some partitioning information, and we can use that for future queries. And as I said, all this happens while we process the query. So let's see, second step. Another query arrives on the same column but requests slightly different range. Now it says, give me everything between 7 and 16. So now 7 fits, it will drop into the first green piece over there. Okay? So what we do, we go ahead and we play the same trick. So we split this into two pieces, everything smaller than 7, everything bigger than 7. So again, using the query request as an advice of how the data should be stored. Then as we go through the column, we realize that the next piece, it is actually contained within the result. So now we can skip this piece. We don't have to touch this data. And if you remember, I talked before about how touching data is actually the most important part, not computing data. So since we can skip data, now we're becoming faster. And then we go to the next piece, and this is where 16 falls in. And again, we just split this into two new pieces. Everything smaller than 16, everything bigger than 16. And basically, we get the same effect as before. We just collected all results for this particular query in a contiguous area. It just happens to be 3 conceptual pieces now, but still it's a contiguous area. We can look at it as a single piece. So this is the same thing that binary search would give you. But more crucially, now we have even more knowledge about how the data is organized. And we do that based using what the queries request. Okay? And you can see that as this keeps working like that, basically we keep creating more pieces, the pieces become smaller, we have more opportunities to skip data. Since we're skipping data, this thing becomes faster. Okay? And this goes, this is about just a simple operation, about what happens inside the DB system. Think about applying ideas like this to every single algorithm, every single data structure that exists in a data system, and actually making it work together also for updates and also to all these challenges that we have in data systems. So I'm just going to give you a performance point from a recent experiment that we did using Sky Server data. So basically, we took original Sky Server data and original user queries, and we played it in the same exact order that they arrived in the. I'll try. And we found out that we could actually process 160,000 queries by the time an original system hasn't answered anything, 0 queries. Okay, so that gives you a feeling about how what techniques like this can give you. Okay, so this is what we say, what we mean when we say minimizing the data to query time. Okay, so same techniques we can apply, for example, we apply to other kinds of models. So this goes about relational data. We applied same techniques on data series processing. And the idea is, for example, that you just go to a pile of sequences of data series, and you just start building the complex indexes to do subsequent matching on the fly while you process queries. Okay, and we get performance examples like this. So on the left is state-of-the-art, best possible the data sequence indexes, and you see that doing things in an adaptive way to free data exploration, we can be 6 times faster. And since data is big and processing data takes in the order of hours, being 6 times faster is actually very important. In this case, 2 hours instead of 12. Okay, so since I have only a few more minutes, I'm going to skip a few slides and go all the way to the end to my very last idea. So this is something that we just started. The more we go into this, the more we try to play with these adaptive techniques, the more we find that there's so different kinds of options that just the space just explodes. Okay, so we just started this new project where basically we're thinking we're going to adopt techniques from the theory of evolution and think about how we can use experience from genetic algorithms and bridge this together with systems. And as I said before, it's not about figuring out how we can make one specific algorithm adaptable and interactive and so on and so forth, but how you can make the whole system. So this is not about really optimizing a single algorithm, but optimizing the sets of algorithms and data structures that you're using together, which is a much more complex and much more interesting, much more challenging problem. Oh, and where does this apply? One first area where we're trying to apply this is diverse hardware. Okay, hardware keeps evolving. Think about big clusters, different hardware, diverse hardware. Yet you're using a single data system, which has specific data structures, specific algorithms, but not all parts of this huge cluster play optimally with this specific data structure and this specific algorithm. So what if you had a system that for every different node that just goes and sits, it can optimize optimally itself in an evolutionary way for this specific hardware. And optimally would mean that, for example, choose optimal node sizes for your data structures based on your cache sizes, based on the properties of your RAM, or the CPU, and so on and so forth. And I want to leave you with two thoughts. First of all, I was trying all this time to pitch these ideas to you as that this is going to be something very useful for the future. And as much as this is true, these ideas are also useful for now. Because complex systems requiring huge administration efforts and maintenance efforts, basically they translate to a huge financial overhead, both for, even if you're a huge company and you can afford it, it's always nice to spend less money. So these ideas actually apply also today. And the second part is that definitely the more we look into this, it's definitely something that we cannot do alone. It's something that ideas like this and efforts like this should span across all computer science and definitely all sciences. And this is, at least in my opinion, this is one of the opportunities of big data, people working together and realizing that people should work together. So that's it. You can find more about our work at the DASLab website at CIS at Harvard. Thank you.
You have one question?
Yeah, sir, when you're talking about the adaptive indexing, is there at some point that it starts to failing if the type of queries or is too different? I mean, if you're trying to solve a problem where you cannot really learn from the system.
Yes. Yeah. So yes and no. There are cases where this is true and cases where this is not true. So for example, for the very simple case operation that I just showed you, where you're just trying to conceptually sort a column, basically whatever you do is useful. Because any kind...
At the time of changing, of reorganizing it, also like that.
So the time adds up, but I mean, I didn't show you examples, but based on the way that you're doing it, so as long as you're concentrating within, let's say, cache sizes or memory sizes, you can do this very efficiently. For example, one data point is that, let's say when you are within the cache, you don't have to sort the data. A scan is equally fast. So since a scan is equally fast, as a binary search, you can scan and reorganize your data at the same cost of binary searching, for example. So you can hide a lot of this cost for local operations. And then for operations where doing random things, let's say arbitrary actions, can potentially be an overhead. One idea that we're exploring, and we have some first results on that, is how we can, as things are happening, we don't really, we go, just saying that we're going to react only on what users do is an extreme approach by itself, right? So we also have some hybrid techniques where we're not only reacting to user requests, but also we are monitoring the system in between user requests, and we try to plug in more smart actions that are sort of going to balance what is happening. So it's something in between again.
It's getting the way you make decisions, but it's not just driving the policy.
Yeah.
Thank you very much.
Thank you.
Oh, yeah. Okay. Sure.
Can you come here?
We have a certificate for you.
Okay, so good morning. We want to acknowledge and appreciate today's morning keynote speaker, Dr. Stratos Idreos from Computer Science, Harvard School of Engineering, Applied Science, Harvard University. I request Dr. Justin Jihan, Conference Steering Chair, to give this appreciation certificate. Can you come?